Hello everyone, this is our presentation for EEE 473 Medical Imaging Project, which is an MRI simulator. We will present you our project. The presentation will be held out by me, Orkun Bedir, and my partner, Bediz Güngör. So magnetic resonance imaging is one of the most frequently implemented imaging techniques, and the components that are included to function synchronously in generating a magnetic resonance scanner are RF coils, gradient amplifiers, and various software artifacts. So our project is an implementation of magnetic resonance imaging simulator, and it's crucial to indicate that taking the constraints and the resources that are provided under consideration, the project is constructed purely via software implementation. And to state again briefly, the main focus of the project can be indicated as generating a magnetic resonance imaging simulator and MRI simulator on one of the widely used software environments, namely MATLAB. So proceeding with the methods that we have embraced, we will explain you the implications that we have gone through on dataset. We will explain you the slice selection procedures that we have embraced. Also, we will give you descriptions about the non-idealities that we have taken into account to make our project more realistic, and also as we have proposed to include. And we will also give you a detailed description of the approach that we have embraced throughout implementing our project.
We have used the dataset of McGill. They are proposing a dataset of anatomical model of normal brain, and there are 181 brain images from different slices with dimensions of 181 to 217 inside. And the dataset is discrete, and at each voxel the tissue types are labeled, as you can see on the right side of the slide. Since the dimensions were not equal, which made x and y dimensions equal by adding zeros, which corresponds to background. The reason why we choose this dataset is because this dataset is discrete, and McGill provides tissue parameters for each tissue type, which are T1, T2, and T2 star, and proton density. We made slice selection by assuming we gave an RF pulse signal, but we didn't actually implement it like that. We assumed the slice center is at 93 millimeter and slice thickness is 1 millimeter. Instead of forming Larmor frequency matrix, we take 93rd index of the dataset. And we continued with that image.
Proceeding with the non-idealities that we have taken into account, the first non-ideality that is taken into account is the chemical shift. So chemical shift occurs due to the issue of the hydrogen in fat is shifted down by 3.35 parts per million with respect to the hydrogen in water, thus resulting in the following alterations in the system of MRI simulator, which can be seen below. So the alterations occurring due to the chemical shift is added to the molecules, specifically added to the molecules that are classified under the portion of white matter throughout the human brain. Due to the myelinated fibers in the white matter, white matter is the portion of the brain that has the highest relative concentration of fat molecules. The second non-ideality that we have taken into account is inhomogeneity, as proposed, inhomogeneity of the magnetic field, which was proposed. Magnetic field is to be obliged to be very homogeneous in MRI scanners, but also in practice, it's also frequently observed that we have 1 parts per million variations per Tesla of inhomogeneity in MRI scanners.
For the approach, we used equations that are presented in the left side of the slide. We used transverse magnetization to display magnitudes of transverse magnetization, and we use longitudinal magnetization in order to obtain effective spin density, and with integrating effective spin density while updating longitudinal magnetization with repetition time and previous longitudinal magnetization, we obtained the received signal. After that, by multiplying it with the demodulation signal, we demodulated, and after normalizing the signal, we obtained the k-space data. By taking the inverse Fourier transform of k-space data and normalizing it, we obtained desired axial image.
Proceeding with the results. So throughout the results section, you will see the magnitude of the transverse magnetization on the left side. You will see the k-space sampling on the middle, in the middle, and you will see the axial image of the brain, the reconstructed image on the right side. So for the first one, I'll give you a detailed explanation. For the others, I'll give you brief descriptions, and a comprehensive discussion will be made in the discussion part after showing you the results. So on the left side, we have the magnitude of the transverse magnetization. In the middle, we have the k-space sampling. And on the right side, we have the reconstruction of the image with desired axial proton density weighted image of the 93rd slice without chemical shift and inhomogeneity with spin echo. Here you can see the magnitude of the transverse magnetization, the k-space, and the desired axial proton density weighted image of the 93rd slice without chemical shift and with the contribution of inhomogeneity using gradient echo. Here you can see again the same reconstruction procedure without chemical shift but with inhomogeneity, but this time with embracing the reconstruction technique of gradient echo. This time you can also see the reconstructed image without the contribution of chemical shift but with the contribution of inhomogeneity while embracing the technique of spin echo. This time you can see the effects of chemical shift and inhomogeneity at the same time simultaneously when the reconstruction technique of gradient echo is embraced. And here you can see the same thing, the same situation with spin echo. Proceeding with the conclusion and discussion. So the images of picked slice of the human brain from the dataset is correctly and fully reconstructed and displayed as can be observed from the results section. Regarding the concept of image quality, the reconstructed images without the contribution of the effects arising due to non-idealities can be classified as properly reconstructed. Without the non-idealities, without the contribution of non-idealities, one can also state that they are not one-to-one. But this is something typical, as we can sometimes see line artifacts in real life too, while dealing with magnetic resonance imaging. So alterations in means of the locations of the pixels containing white matter can be observed when compared to the corresponding pixel locations throughout the ideally reconstructed image. The effects of the chemical shift mainly resulted in erroneous reconstructions of the tissues classified as white matter as shifts in locations throughout the image which satisfies the theoretical expectations. So this is a local shift because the chemical shift is added to the pixels, to the components that are classified as white matter throughout the dataset. The theoretical expectation regarding the effects of inhomogeneity is the observation of a slightly inaccurate and blurry image, as inhomogeneity causes the simulator to erroneously pick the data points while reconstructing the image. What I mean by that is that while reconstructing the image from the data points set on k-space, the simulator is prone to make erroneous selections by picking various data points from the unselected slices that are located slightly below or above the slice of interest. So it's crucial to state here that the implementation of the reconstruction process is made under the assumption of picking the slice of interest directly from the dataset. So in order to be able to observe the effects of inhomogeneity, in our case, a random Gaussian noise is added to the picked slice before reconstruction. It's also crucial here that we added it before reconstruction to make it realistic. To be able to have a I stated that. So it can be observed that the reconstructed image is blurred in the case of the contribution of inhomogeneity and contains erroneously reconstructed pixels and several additional line artifacts, which once more is in parallel with the theoretical expectations. In turn, highlights the appropriate implementations that are made throughout the project in examining the effects arising on the reconstructed image due to the presence of inhomogeneity. Thank you for your considerations. Thank you for your time. This is our presentation. These are our references. Thank you for your